It's going to be the lecture over sections 30.3 and 30.4. So the two most common decay modes are going to be the emission of alpha and beta particles. Now, an alpha particle has two protons and two neutrons bound together with zero total spin. Alpha emissions occur principally with nuclei that are too large to be stable. So an alpha particle, again, the same thing as a helium nucleus, is basically used when you have large nuclei that are unstable and need to get rid of some of the instability within the nucleus. And so they shoot out an alpha particle. So that's typically where you're going to see that particular type of reaction. The beta particle, or more specifically the beta minus particle, is an electron. The antineutrino is also involved in the process of beta minus decay, represented right here. And this is when a neutron becomes a proton. When that happens, then you end up seeing a beta minus, an electron that goes along with it. Why would that happen? Again, remember that you're going from something that is electrically neutral to something that has, in its balance, is also electrically neutral. So if you're going from a neutron to a proton, you've got to be able to conserve charge. In order to be able to conserve charge, once you create a positive charge, you also have to have something there that's got a negative charge to go with it. The rate of decay of an unstable nucleus is described by the decay constant, lambda. If the number of nuclei at t is equal to 0 is n naught, then the number remaining at time t is going to be this. So in other words, this is what you start out with. It's going to have an exponential decay. That decay constant there is going to be part of the exponent. And this is going to be the amount that you end up with that mathematical function. Now, the half-life is going to represent the time required for half of the nuclei to decay. It's going to be related by the decay constant in this fashion. So in other words, your half-life is going to be the natural log of 2 divided by lambda. Radiation exposure can cause cancers and genetic defects, yet it can be used effectively in medicine for intentional selective destruction of tissues such as tumors. Radiation can also help diagnose a problem. So injecting low doses of a radioactive isotope into the body can create images of potentially problematic regions where the radioactive material builds up. So in other words, things like PET scans and whatnot can tell you where activity is going on in the body, and if that activity is something that needs to be treated, then we'll know about it. Okay, so we've already discussed radioactivity, and we've discussed nuclei that are too big to remain stable. We've talked about alpha particles and the two most common decay modes, which is alpha particles as well as beta particles. Radium is an example of an alpha emitter. The speed of the emitted alpha particle can be determined from the curvature of its trajectory when it passes through a magnetic field. Speed turns out to be about this. And although that's fast, it's not, it's only about 5% of the speed of light. So you can use non-relativistic kinetic energy expressions. The alpha particle mass turns out to be this. So the kinetic energy using this particular formula can be determined here. So you've got this radium nucleus here, and all of a sudden it spits out an alpha particle. And so you've got radon, which is something in and of itself you have to worry about. And then you've got the alpha particle heading off in this direction, obviously headed in opposite directions in order to be able to conserve momentum. So alpha particles are always emitted with a definite kinetic energy determined by conservation of momentum and energy. It can travel several centimeters in air or a few tenths or hundredths of a millimeter through solids before they are brought to rest by collisions. So early in the 20th century, it was established that a beta particle is actually an electron. You might ask how a nucleus can emit an electron if there aren't any electrons in the nucleus. The emission of a beta particle involves a transformation of a neutron into a proton as well as an electron. So even a free neutron decays into a proton and electron with an average lifetime of about 15 minutes. And so today, this emitted particle is called a beta minus particle to distinguish it from another particle, the positron, which is basically an electron, but with a positive charge, as if you needed more to worry about. So beta minus decay usually occurs when nuclei for which the neutron to proton ratio is too great for its stability. So in beta minus decay, N increases by 1, N decreases by 1, Z increases by 1, and the total number of nucleons doesn't change. So both alpha and beta minus emission by changing the Z value of a nucleus have an effect of changing one element into another, which if you were an alchemist, you would love to be able to do that en masse. With a nucleus that has a neutron to proton ratio that is too small, it may emit a positron, increasing N by 1 and decreasing Z by 1. Beta particles can be identified and their speeds measured by the curvature of their paths in a magnetic field. I've heard that one before. The speeds are pretty close here to the speed of light, so you've got to use relativistic calculations on this. Now, if only two particles were involved and the recoiling nuclei, in other words, the beta particle and the nuclei were the only two particles involved, conservation of momentum and energy would require each to have a definite energy. But the beta minus particles are found to have a continuous spectrum. So in 1930, Wolfgang Pauli proposed that the third particle, electrically neutral and unseen, must be involved. And Enrico Fermi christened this particle the neutrino. They didn't observe it until 1953, although by then its existence had been firmly established by indirect evidence. Today, this particle is called the antineutrino. The basic process is written here, as we saw in the summary. After alpha or beta emission, the remaining nucleus is sometimes left in an excited state. It can then decay to its ground state by emitting a photon, also often called a gamma ray photon or simply gamma. Typical gamma energies are 10 keV to 5 MeV. For example, alpha particles emitted from radium have two possible kinetic energies corresponding to a total released energy of this or this. When an alpha particle with the smaller energy is emitted, the resulting nucleus is left in an excited state, which then decays to the ground state by emitting a gamma photon with energy. And that's what it's trying to display here. With radioactive nuclear decays, the resulting nucleus may also be unstable. In these cases, sometimes it takes a while to get a stable nuclei to come about. The most abundant radioactive nucleus found on Earth is uranium, which undergoes a series of 14 decays, 8 alpha emissions, and 6 beta minus emissions, terminating at lead. You've got another Segre chart here. In alpha emission, N and Z each decrease by 2, and beta emission, N decreases by 1 and Z increases by 1. And the half-lives of the individual decays are given in years, days, hours, as you can see here on the chart. So you can see here uranium decay, bouncing to all different kinds of elements over time, eventually terminating here at lead. So for the rates of decay, if N is going to be the number of radioactive material in a sample at time t, and that change in N is the negative change in the number during this short interval of delta t. So the rate of change is a change in N over the change in t. The larger number of nuclei in the sample, the larger is the number that decay during any interval. So the rate of change is proportional to N. So in other words, it's equal to some constant multiplied by n. If you go through and if you solve, doing some mathematics, you come up with this particular equation, which tells you the number of radioactive nuclei remaining after time t. The half-life and the decay constant are related in this fashion. Radioactive or radiocarbon dating is basically taking advantage of decay constants and how much material is left in a body to determine how old it would be before. The unstable isotope carbon-14 is produced by nuclear reactions in the atmosphere caused by cosmic ray bombardment. Thus, there is a small portion of carbon-14 and the carbon dioxide in the atmosphere. Plants that obtain their carbon from this source also contain the same proportion of carbon-14 as the atmosphere. So when the plant dies, it stops taking in carbon, and the carbon-14 is already absorbed, starts to decay with a half-life of this number of years. By measuring the proportion of this in the remains, we can determine how long ago an organism died. So similar techniques are used with other isotopes for dating geological specimens. Some rocks contain the unstable potassium isotope of potassium-40, which decays to argon with a half-life of this long. The age of the rock can then be determined by concentrations of potassium-40 and argon-40. So you've got some problems there and some solutions there that you can go through. Now, let's go on to 30.4. I don't know why it does what it's doing. Radioactivity is basically going to be defined using these particular terms, and electromagnetic radiation is going to be defined using this. So the difference here may be a little bit hard to see, but we'll get used to it as we go along. As these particles pass through matter, they lose energy, breaking molecular bonds and creating ions, hence the term ionizing radiation. Charged particles interact through direct electric forces on the electrons. X-rays and gamma rays interact by the photoelectric effect, in which an electron absorbs a photon and is freed from its molecular bond, or by Compton scattering. Neutrons cause ionization indirectly by colliding with nuclei or being absorbed by nuclei with subsequent alpha or beta decay of the resulting unstable nucleus. So you can see here some examples of using what we know up to this point to kind of date samples like this. The interactions of radiation with living tissue are extremely complex. So the quantitative description of the effect of radiation on living tissue is called radiation dosimetry. The absorbed dose of radiation is defined as the energy delivered to the tissue per unit mass of tissue. It's going to be basically a joule per kilogram, and it's called the gray. So a gray is defined as a joule per kilogram. I don't know that a rad is used as much as the gray is currently. I think at the time the textbook was written, a rad was something that might have been used, but a gray is more commonly what you would see now. The effect of radiobiological effectiveness, or RBE, tries to take certain things into consideration. The absorbed dose isn't an adequate measure of biological effect because equal energies of different kinds of radiation cause different degrees of biological effect. So X-rays with 200 keV are defined to have an RBE of unity or 1, and the effects of other kinds of radiation can be compared experimentally. So in other words, they're trying to get at what kind of biological damage can be done for these different types of particles. So you have equivalent dose where you take the absorbed dose and multiply it by the radiobiological effect, what you see up here. In REM, you can do the same thing here. It's just your absorbed dose is going to be considered to be rad. And this effective dose here is going to be in sieverts. This is going to be considered to be in REM. Ionizing radiation is a double-edged sword. It poses serious health hazards, yet it also provides benefits. You can diagnose and you can treat disease with certain applications. So an ordinary chest X-ray delivers about 0.2 to 0.4 millisieverts to about 5 kilograms of tissue. Radiation exposure from cosmic rays and natural radioactivity in the soil is on the order of 1 millisievert per year at sea level. And if you're up at 1,500 meters, then you're looking at about twice that. And there's a number of hazards that go along with radiation exposure: genetic defects, cancers. And you know, what is considered safe? Well, you do have certain government publications that will give you an idea as far as what is considered to be safe. Maximum yearly exposure for the general public, you're looking for 2 to 5 millisieverts. Those that work in the profession are permitted up to 50 millisieverts per year. Are they too high? Well, obviously any exposure is not something that you want, but you've got to draw a line somewhere. And this is an example of somebody who is undergoing a gamma knife, where you have several holes in the helmet that are trying to target a particular tumor. If it looks like you've got somebody here who's being anchored as they are being put into the helmet, that's exactly right. Sometimes these frames are actually screwed to the head. It's not a very pleasant experience, but when you got a brain tumor, what are you going to do? So again, something like this is a PET scan where, again, you can see, or in this case, I guess it is, let's see if I can find it. Yeah, it's a radioisotope technetium-99, where it goes into the body, and you can start to see where the material will accumulate, and you can see it looks like there might be something going on, maybe in these bony areas right in here. So this is again, this is an application of the types of reactions or radioactivity that we see. Yes, it can actually be useful in many cases.